This exercise, we will investigate how Thevenin theorem works with circuits. And so what we're going to do now is I'm going to draw a circuit and justify why Thevenin is a good idea, and then show how to do it. Okay. Now let's suppose we have a circuit like this. Usually the circuits can be quite complex, which means they have a lot of different kinds of sources, like voltage sources, current sources, something like this. And everything is relative to some sort of a load, right? So let's suppose we had this circuit right here. And I'm going to put these 2 points here. These are going to be my little references to show where the load is typically connected, okay? So all of this is one system, okay? So this would be RL, for example, okay? Here, okay, we can give a value R1, maybe R2 here. This would be an I, this would be an E, okay? So the point of all this is this. So how does RL, as a resistor, sees the system? Okay, so the system right here is like this. So it's connected to it. What we want to simplify all of this into something maybe with an internal resistance and some sort of a voltage source right here. So everything you see here, if we could abstract it into this system where we have an E equivalent, we're going to call it ETH now. That's going to be Thevenin, and RTH. So these are the famous words, Thevenins, that you've heard of about. So let's hope I'm spelling this correctly. Okay, so this is Thevenin. Okay, so as far as RL is concerned, between A and B, it sees a resistance, an internal resistance to the system, and an internal voltage source. Okay, so we want to accomplish that goal, which makes it easier after that to figure out, okay, well, what is our IL? What is the actual VAB here? Maybe what is the power consumption here for RL, etc., etc. Okay, so the way to do this, you're going to do this in several steps. The first thing you want to do is find RTH. So what is the Thevenin equivalent resistance as seen by RL in this direction? To do this, there's a simple technique. So how do you do it? What you do is any voltage source you will short, and any current source you will open. So let's look at this circuit again here, right here. Right? So you have a current source right here, and you have R2 right here. So that's part of the system. And your point A and B are right here. Right? So we're looking at it from this point of view. And we're interested in RTH at this point, looking at it this way. And the way we're going to do this is, as I said, we're going to short the voltage source and open the current source. So what does that lead? That will lead to a circuit like this. So can we put R1 here, since the voltage source is shorted, right? I'm going to put B as my reference here, so I could do this. Here's my reference here. And then open up the current source. So it's open, nothing there. And then have R2 here. Okay? And this is point A, and this is point B. So what is the total resistance seen from this end? Well, RTH, in this case, will be equal to R1 in parallel with R2. That's how it sees the circuit for this configuration. Obviously, if we had a different kind of network, we could have a combination of series and parallels. Again, all depending on what happens when you short your voltage source and open your current source. Obtaining a circuit of this nature, looking at R total from this angle. Okay, so RTH again, so if you had to do this mathematically, will be R1 times R2 Okay, so just plus R1 plus R2 here. Okay, good. B. Now you're going to do a couple things. You're going to leave the current source open, but you're going to put back the voltage source. Then we're going to do the other way. We're going to short the source voltage and put back the current source. So for now, we're going to put back our voltage source right here. Here is R1. Here is R2. Here's point A and B. And this is E right here. Now, obviously, the current source is open. So if you look at it this way, this is where it would have gone. But it's an open circuit. Okay? Again, I'll reference here if you want to do that. So what we're interested in here is what is the voltage seen from this point. All right? So we're looking at VAB1. Now, do not confuse that when we're done, okay, with the total VAB that's in here. This is going to take us to what will be our voltage source when for the Thevenin equivalent circuit. Okay, so VAB1, as we can see, it's simply a voltage divider. So VAB1 is going to be equal to E times R2 divided by R1 plus R2 based on this configuration. Excellent. So now, let's go ahead and short the voltage source. Okay, so we short that, put the resistor back down versus ground here, or your reference point, right? So here's your reference point. And let's put our current source back in here. Now this thing was pointing up, that's fine. And you have R2 here, and you have the point A and B here. So A and B, right? Okay, so we're looking now at VAB2, right? So we want to know what is the voltage drop against R2? Well, we could use the current divider rule, because remember this I here is going to have a portion that goes this way and a portion that goes that way. In other words, if you really wanted to look at it in a different way, you could put your current source here, since they're all in parallel, and you have two parallel resistors, right? So that didn't change vis-a-vis A and B. Same reference, A and B. And this would be R2, this would be R1, and this would be I. Now, obviously this current will be coming into this node and split right here, right? And recollect from here. So what is IR2? Well, IR2 is going to be important because VAB from this point will be R2 IR2. So VAB here, let's call it VAB2, will be equal to IR2 times R2. Well, what is this IR2? This IR2 will be equal to current divider rule, I times the other resistor, R1, divided by the sum of the resistors. Aha. So that means you're going to end up with, so you can take this up right here. So it's I. So IR2 is I times R1. Okay. Everything times R2 divided by R1 plus R2. Okay, so that would be the partial current, or the partial voltage between A and B. Okay, so what is ETH? ETH is going to be the sum of the two. So this ETH here is going to be equal to VAB1 plus VAB2. Okay, so you're going to add this quantity to this quantity, and notice you have constants. This is a constant, this is a constant. And not only that, you know these values, R1, R2, R1, R2. So these are well-known values. So you can actually put ETH will be equal to E times R2 divided by R1 plus R2 plus I R1 times R2 divided by R1 plus R2. Now, they happen to be the same denominator. So if you want to simplify this, okay, we can factor the R2 divided by R1 plus R2 times E plus I. So you're going to multiply E by R2 with this factor and I R1. Now remember, this is a voltage. This is a voltage, so that's good. And that would be your final VTH right there. Okay, so we have this, and then we have ETH right here. So that would be ETH for this circuit. So now if you have to redraw this, okay, so let's do it here. So you would have ETH here, whatever its value is, and then RTH here. But now, between A and B, you have a new circuit with RL here. And if you were to look for the current load, IL, well, that would be ETH divided by RTH plus RL. Okay, now if you want the true VAB from here, well, that would be your IL times RL. And that would be the VAB that you would want from the system.